Last lesson ended on a gap. A coin that lands heads 70% of the time has entropy 0.88 bits. Model it as fair, and you pay a full bit. That extra 0.12 bits is the entire subject of this lesson. It has a name, the kullback-leibler divergence. It measures, in bits, exactly how much you lose by believing Q when the truth is P. The definition is the subtraction we just did. D of P from Q equals H of P, Q minus H of P cross entropy minus entropy. The total cost, minus the part that was never avoidable. Expand it, and the two logarithms combine. D equals the sum over x of P of x times log of P of x over Q of x, which is E under P of log P of x over Q of x. The average log ratio between the two distributions. Read it as the excess. Entropy is the bits you must pay because the world is genuinely random. Cross entropy is the bits you actually pay. The KL divergence is the surcharge, everything you pay purely for being wrong. 3 properties, and the first is the one you will use most. D is always at least 0, and it equals 0 if and only if P and Q are the same distribution. That is Gibbs. Inequality restated. The surcharge can never be negative. Second, it is not symmetric. For our coin, D of P from Q is 0.12 bits. Swap the arguments and you get 0.13. Close here, but in general the two can differ enormously. Because it fails symmetry and fails the triangle inequality too, it is not a distance, which is exactly why it is called a divergence and not a metric. Third, it can be infinite. If Q assigns 0 probability to an outcome that P actually produces, the log ratio blows up and D is infinite. That is precisely the absolute continuity condition from lesson 57, and in that language, D of P from Q is the expectation under P of the log radon-Nikodym derivative. The asymmetry is not a technicality. It changes what you get when you fit a model. Suppose the truth P has 2 separate peaks, and your model Q is a single Gaussian, which simply cannot represent both. Minimize the forward direction, D of P from Q. The sum is weighted by P, so anywhere P has mass but Q has almost none is punished severely. The safest thing Q can do is stretch to cover everything, including the empty valley between the peaks. That is mass covering. Now minimize the reverse, D of Q from P. The weights come from Q itself, so Q is only penalized where Q puts mass. The safe move is to hide inside one peak and ignore the other entirely. That is mode seeking. Same 2 distributions, opposite answers, and that is exactly the difference between maximum likelihood and variational inference. The KL divergence, D of P from Q, equals the sum of P times log P over Q, which is cross entropy minus entropy, the bits per symbol you pay purely for believing the wrong distribution. Non-negative, 0 only when the distributions match, infinite when Q rules out something P still does, and asymmetric, forward KL covers the mass, reverse KL chases a single mode. Next, point that machinery at a joint distribution. The KL divergence between a joint and the product of its marginals is mutual information, a measure of dependence that catches everything correlation misses.